For most of modern astronomy, the story of comets has been pleasantly simple. They were the dirty snowballs of the solar system, fragile mixtures of ice, dust, and rock that flared briefly when they wandered too close to the sun, then quietly crumbled back into the dark. That story was comforting because it repeated itself over and over again. From Halley to Hale Bopp, from new survey discoveries to faint visitors barely noticed, the physics fit the same script of low density, porous bodies, chaotic shapes, and jets of vapor spraying out in random directions. Then 3i Atlas arrived, and the last 48 hours of data have tugged on a loose thread in that old story. The orbital calculations still say that 3i Atlas is an interstellar visitor falling along a graceful curve past the sun. Yet the way it answers, when we illuminate it with radar and spectrometers, refuses to match the expectations of a dirty snowball. It is as if the universe has quietly slipped a different kind of object into a familiar role to see if we would notice the mismatch. When powerful ground-based transmitters paint 3i Atlas with radio waves, the returning echo does not look like the scatter from a lumpy rock. Instead, it flashes back in concentrated bursts, almost as if a smooth surface had swung momentarily into perfect alignment, catching the beam like a mirror and sending it straight home. The signal spikes are sharp, bright, and short-lived, the kind of radar response more often associated with aircraft wings or polished metal structures than with the rough outlines of a cometary nucleus. On top of that, the spectrum of sunlight reflected from 3i Atlas bends into a strange, sleek curve. Where astronomers expect the fingerprints of silicate dust and organic frosts, they find instead the broad, cold gleam of metal. The absorption features line up most closely with nickel-rich alloys, the same class of materials we use in turbines, heat shields, and high-temperature components when we want something to stay solid in impossible heat. It is an odd thing to see in an object that was supposed to be made of ancient, unrefined debris. This is where chemistry quietly becomes a character in the mystery. Natural iron meteorites that fall to Earth almost always carry a majority of iron, with nickel as a minor partner. That ratio is a kind of cosmic habit, a fingerprint of how metals separate and cool inside forming planets and asteroids. In 3i Atlas, the early analyses hint at an inverted balance, where nickel may rival or even exceed iron, a recipe that feels less like primitive rock and more like the careful tuning of a metallurgist, planning for strength, toughness, and resistance to heat. The first lesson of 3i Atlas is not that we have discovered an alien machine. It is that our standard mental picture of an interstellar comet may be too narrow. When an object shrugs off heat, reflects radar like polished steel, and advertises an unusual metal mix, the phrase dirty snowball stops being an explanation and becomes a question. What else have we been missing, simply because we assumed that every visitor from the dark would conform to the few examples we have touched and photographed up close? That is where this channel lives, in the quiet space between comforting models and uncomfortable data. Here, we let the instruments speak slowly, we trace their lines with patience, and we treat every anomaly not as a jump scare, but as an invitation to think more carefully about how the universe really builds its objects. This is a place for long arcs of reasoning, for gentle doubt, and for the kind of curiosity that can sit with not knowing the full answer for a very long time. If you find a strange kind of peace in that process, you are welcome to stay with us. You can let these long-form investigations accompany your evenings, your work, or the drift toward sleep, a steady murmur of physics and possibility in the background of your life. Subscribing, leaving a quiet like, or sharing the episode with someone who loves astronomy helps more people discover this slower way of exploring the sky, where questions are allowed to remain open as we gather more evidence. You can also be part of the ongoing investigation. In the comments, you might tell us whether you lean toward a natural explanation for the high nickel signature of 3I Atlas, or whether you suspect an engineered surface hiding beneath a coating of interstellar dust. You might share the one question about this object that keeps circling in your mind long after the screen has gone dark, and read what keeps other listeners awake as they listen under their own patch of sky. Now, dim the lights. As the room around you settles into shadow, imagine the faint tracking lines on a monitor in a control room somewhere on Earth. Each night, small teams quietly follow 3I Atlas, stacking frames, refining its path, replaying its echoes, trying to decide whether the oddities are merely noise or the first hints of something new. Outside their windows, the night looks calm, but on their screens, the data is whispering that one particular point of light is not behaving quite like the others. In the classic picture of a comet, bulk density is low, ice is plentiful, and dust clouds peel away as it nears the sun. Radar returns are soft and scattered. The surface is uneven and chaotic, shaped by countless impacts and fractures over billions of years. That template has worked well for decades because almost every object we have studied up close has agreed with it, from short-period comets near Jupiter to long-period visitors plunging in from the distant Oort cloud. 3I Atlas does something different. It glows without shedding much dust. Its spectrum leans toward metals instead of minerals. Its radar cross-section behaves as if large, coherent surfaces are rotating in and out of view, presenting broad facets one moment and narrow edges the next. No single measurement is conclusive on its own, but together they trace the outline of a possibility that our textbooks did not prepare us for, a possibility in which at least part of 3I Atlas behaves less like stone and more like hull. As we unfold this first part, we will stay close to the numbers and the physics. We will ask at how reliable these measurements are, what they rule out, and what they leave intriguingly open for later sections. For now, hold on to one simple idea as you listen. Perhaps, somewhere in the dark between the stars, not every wandering object is rock and ice. Perhaps some of them are built to last. Chemistry does not usually feel dramatic. On paper, it is just symbols, ratios, and careful curves. Yet in the case of 3I Atlas, a handful of quiet numbers has become one of the loudest parts of the mystery. If the motion of 3I Atlas tells us where it is going, then its spectrum whispers what it is made of, and that story does not match the usual script for a wandering fragment of rock and ice. On Earth, iron meteorites have been our main laboratory for understanding metal-rich bodies in space. When these heavy visitors fall through the atmosphere and land in deserts or ice fields, we cut them open and measure their composition with great precision. Time after time, the same pattern emerges. Iron dominates, usually around 9 parts out of 10. Nickel is the loyal companion, a minor element that makes up the final part of the alloy. This majority iron, minority nickel mix is so consistent that it has become a kind of signature for natural metal separated inside ancient asteroids. To understand why, it helps to picture a young world in cross-section. In its early molten youth, heavy elements sink inward. Iron and nickel melt and flow, forming a bright interior ocean around a forming core. As that ocean cools over millions of years, crystals grow, metals separate, and patterns form. Iron tends to be slightly more abundant, so it takes the lead. Nickel folds into its structure, strengthening and stabilizing, but rarely taking over. The result is a planetesimal core that is mostly iron, with enough nickel to change its properties, but not enough to invert the balance. When 3I Atlas first entered the reach of sensitive spectrometers, the expectation was simple. If 3I Atlas was a typical metal-rich body, the spectral lines of iron should dominate, with nickel playing a secondary role. Instead, early analyses, including those attributed to instruments like CRISM on the Mars Reconnaissance Orbiter, suggested something stranger. The relative strength of nickel features appeared unusually high. In some reconstructions, nickel rivaled iron. In others, depending on the model, nickel seemed to take the lead. Spectroscopists are cautious people. They know how easily noise, calibration errors, and assumptions about grain size can twist a spectrum. So they cross-check. They compare data from different instruments, different nights, different viewing angles. In the case of 3I Atlas, the details still carry uncertainty, but one trend has persisted. Whatever exact recipe we assign to the surface, it is not a standard iron majority. The metal mix looks shifted toward nickel in a way that stands out when you place it next to the catalog of ordinary meteorites. Here on Earth, when the engineers want metal that will not soften in turbine engines or rocket nozzles, they move in exactly that direction. They create superalloys, blends where nickel content is pushed higher, sometimes becoming the dominant element. Nickel-rich alloys hold their structure near extreme temperatures. They resist creep, corrosion, and fatigue. They are what you choose when you know a structure will live near furnaces or stars and must not fail even after many cycles of heating and cooling. There is a quiet discomfort in noticing that 3I Atlas seems to share this taste for nickel. It is one thing to find a metal-rich asteroid. It is another to find one whose composition bends toward the same solutions our own material science reaches for when designing parts that must survive intense heat. It does not prove intention. Natural processes can, in principle, produce unusual alloys under unusual conditions. But it nudges the mind toward comparisons that are hard to ignore. To be fair, there are natural candidates. Bodies like 16 Psyche have been interpreted as exposed cores of ancient protoplanets, stripped of their mantles in violent collisions. Some models of such cores allow for higher nickel fractions, depending on the specifics of formation and cooling. If 3I Atlas is the long-distance cousin of such an object, we might be seeing an extreme, but still natural, outcome of planetary evolution. A fragment of a dead world, cut loose and sent wandering into interstellar space. Yet 3I Atlas refuses to line up neatly even with that scenario. The surface of 16 Psyche, as inferred from radar and light curves, appears irregular, battered by eons of impacts. In contrast, the radar behavior of 3I Atlas hints at smoother, more coherent reflecting areas. Moreover, in places where we expect to see the spectral fingerprints of silicate dust mixed into the metal, 3I Atlas looks unusually clean. The familiar absorption bands of silicate minerals, which light up in many comet and asteroid spectra, are muted or absent. Instead of silicate dust, 3I Atlas appears to shed mainly ions of heavy metals when heated, as if what lies near its surface is already highly refined. There is little sign, in the accessible data of a rubble coating of rock fragments and mineral grains. It is as if someone has stripped away the softer outer layers and left behind a more uniform shell of robust material. In a purely natural context, that demands a specific sequence of violent events: collisions that remove mantles, long exposure to erosive environments, and enough time for weaker components to be worn away. This is where grounded speculation begins. One path says that 3i Atlas is a survivor of deep time, the metallic heart of a long vanished planet, scoured clean by eons in harsh environments until only the toughest alloy remains. Another path suggests something more deliberate, an object that began as metal from the start, chosen and processed to have an inverted nickel ratio because that is what its makers needed. Both stories are consistent with parts of the data. Neither has yet been ruled out. As you listen, you do not have to choose between them. You can simply notice how an inverted metal fingerprint and the absence of common silicate signatures pull us away from familiar categories. 3i Atlas may still be entirely natural, a rare but instructive outlier that will expand our understanding of planetary cores and interstellar debris. Or it may be the first time our instruments have traced, in reflected sunlight, the alloy decisions of a distant workshop. For now, the spectrum keeps its secrets, and the question remains softly open. Are we reading the chemistry of an ancient accident or the materials list of an enduring design? By now, the outline of the puzzle around 3i Atlas is clear. The problem is no longer only where this object came from, but why its surface chemistry behaves like something we already know from our own furnaces. The numbers feel less like the properties of an anonymous rock and more like the specification sheet of a carefully chosen material. When astronomers speak of reading a spectrum, they are doing something similar to a metallurgist in a lab. You shine light, or electrons, or X-rays at a material, and you watch how it absorbs and reflects different energies. Each element and alloy produces a characteristic pattern, a set of dips and rises that act like a barcode. For familiar minerals and metals, those barcodes are already cataloged in libraries. Nickel-rich alloys form a special group inside those libraries. In jets, power plants, and rockets, engineers use them where steel would soften and aluminum would simply melt away. These superalloys are blends that often place nickel in the starring role with carefully measured additions of chromium, cobalt, and other elements. At temperatures where ordinary metals creep and fail, nickel-based superalloys keep their crystal structure intact, year after year, cycle after cycle. In reflectance, that toughness shows up indirectly. The exact shape of a spectrum depends not only on which atoms are present, but also on how they are packed, how smooth the surface is, and whether it has been oxidized, coated, or roughened. A chunk of raw meteoritic metal, pitted and mixed with silicate grains, will not look the same as a forged turbine blade, even if the base elements are similar. Texture matters as much as chemistry. What drew attention in the case of 3i Atlas was that both the composition and the overall curve seemed to lean toward the engineered side of that comparison. The absorption features most consistent with nickel were unusually strong. The inferred surface roughness was low, and when scientists tried simple model fits, mixtures that resembled high-temperature nickel alloys produced better matches than the standard iron-dominated meteoritic recipes. In extreme engineering, this is exactly the corner of material space we already inhabit. Close to the sun, heat is not an abstract number. The Parker Solar Probe, for example, flies through regions where sunlight can heat exposed surfaces to well over 1,000 degrees Celsius. To survive, its designers use advanced composites and heat-resistant metals, arranging them in layers so that the hottest materials face the star and protect the systems behind. Nickel superalloys are not the only solution to such problems, but they are a recurring one. From the throats of rocket engines to the hot sections of gas turbines, they appear whenever we need structural metal to stay strong in intense thermal and mechanical stress. When the spectrum of 3I Atlas hints at a nickel-heavy, corrosion-resistant shell, it is hard not to notice that we would reach for similar ingredients if we were tasked with building a hull to endure star-grazing orbits. It is important, though, to resist the temptation to declare a perfect match. Spectral fitting is a game of approximations. Many different mixtures can reproduce the same broad features, especially when you factor in unknowns like grain size and small surface coatings. There is no single sharp line in the data that says this is Inconel or this is exactly like a specific turbine blade alloy. At best, we can say that 3I Atlas lives in the same neighborhood of composition. Still, neighborhoods matter. If you list the materials that naturally form in cooling planetary cores and compare them to the alloys that industrial civilizations independently invent for high temperature use, you find overlapping regions. The physics is the same in both cases. Electrons, bonds, and crystal lattices obey the same rules, whether they are guided by geology or by engineering. It is not surprising that both nature and technology might favor similar combinations when asked to solve the same kind of problem. From a grounded perspective, one attractive scenario is that 3I Atlas is the metal-rich remnant of a broken world, gradually processed by time into something that behaves functionally like a heat shield. Perhaps repeated passages near stars, combined with erosion in the interstellar medium, stripped away weaker, more volatile materials, leaving behind a dense nickel-heavy skin that now turns its hardest face toward each new sun. In that picture, the resemblance to our own superalloys is a convergent echo, not a signature. Given enough opportunities, physical law sculpts both natural cores and engineered hulls toward the same islands of stability in the space of possible materials. 3I Atlas would then be a kind of fossilized engineering solution produced without engineers, an accident that happens to look like design because the problem it faces is the same. There is, of course, a more provocative reading. If you start from the assumption that some civilizations might send durable probes between stars, you quickly find yourself sketching hull materials that must shrug off both intense heat and long exposure to radiation and dust. Nickel-rich alloys, possibly clad in protective coatings, appear near the top of that list. When we see 3I Atlas reflecting light like such an alloy, the question quietly arises: are we looking at convergent geology or at someone else's material science? For the purposes of this investigation, we do not have to commit fully to either extreme. What matters is that the spectrum of 3I Atlas refuses to sit comfortably in the catalog of ordinary comets and rubble piles. It keeps pointing, again and again, toward a category of matter that is built to endure extremes, whether by the blind patience of planetary evolution or by deliberate fabrication. The numbers do not yet tell us which story is correct, but they refuse to let us look away. As we close this first section, hold that idea gently in mind. Whatever its origin, 3I Atlas carries a skin that behaves like armor, tuned for survival rather than fragility. In the next part of our journey, we will leave the laboratory charts and follow its path past the sun itself, asking how such a hull responds when it actually enters the furnace it seems designed to face, and what that survival can teach us about its true nature. There is a certain kind of courage in flying close to a star. For most of the small bodies in our solar system, that courage is punished. Ice boils, rock fractures, and fragile structures fall apart under the combined assault of heat and gravity. Yet 3i Atlas has already passed its own close brush with the sun, and so far appears to have come through with its shape and spin largely intact. Near perihelion, sunlight is not a gentle glow. It becomes a furnace. The solar flux can climb to many times what we experience at Earth's orbit, bathing any exposed surface in relentless radiation. For an object made mostly of volatile ices, the result is violent. Jets roar from cracks and pits. Material escapes at high speed. In many sun-grazing comets, the entire nucleus disintegrates, leaving behind only a trail of dust and gas where a solid body once traveled. Even more robust rubble piles struggle in this environment. A rubble pile is exactly what it sounds like, a loose collection of boulders, gravel, and dust held together by gravity and weak cohesive forces. When such an object swings close to a massive body like the sun, tidal forces tug more strongly on the near side than on the far side. In the cool outer regions, that imbalance is small. Near the star, it can become strong enough to rearrange or even tear apart the pile. 3i Atlas did not behave like a fragile stack of stones. As it passed its closest approach to the sun on its reported date, models of its orbit and light curve suggest that 3i Atlas maintained a coherent silhouette. The brightness varied as 3i Atlas rotated, but the variations were regular, not chaotic. There were no clear signatures of a sudden breakup, no obvious cloud of debris expanding away from a shattered core. For an interstellar visitor on such a path, that is the first hint that we may be dealing with a more unified internal structure. To understand why that matters, it helps to think about how heat moves. In a porous, low-density body, heat from the sun penetrates unevenly. Some regions stay cooler and retain volatiles. Others warm quickly, venting gas and dust. The result is a patchwork of stresses and eruptions. Meanwhile, the internal strength is limited by loose contacts between grains. When tidal forces and internal pressure combine, things crack and spill apart. A metal-rich monolith behaves differently. In a dense, continuous structure, heat conducts more efficiently. The surface still burns under intense radiation, but temperature gradients can be smoother. Instead of isolated hotspots tearing open, the entire hull warms and cools more uniformly. Nickel-rich alloys, in particular, combine good thermal conductivity with high melting points and strong resistance to creep at elevated temperatures. They do not shrug off heat entirely, but they stay solid and cohesive at temperatures that would wreck ice and most rock. Imagine 3i's Atlas as a solid, nickel-heavy body entering this furnace. The outermost layers absorb brutal sunlight. Some material may vaporize. A thin skin may oxidize or change phase. But beneath that thin shell, the structure remains locked together. The same properties that make nickel superalloys useful in turbines and rocket engines would, by simple extension, make them useful in a body that expects to graze close to a star more than once. There is an earthbound analog that helps fix the scale of the problem. When engineers designed the Parker Solar Probe to dip into regions very close to the Sun, they wrapped it in a heat shield designed to endure a flux far beyond what satellites in Earth orbit face. The shield had to survive repeated passes, holding its integrity even as its sunward face endured temperatures of more than 1,000 degrees Celsius. No ice could have survived such conditions. Only carefully chosen materials made the mission possible. 3I Atlas, of course, was not designed by us, at least as far as we know, but the physics that drove the design of Parker's shield still applies. Any object that moves on a path, bringing it close to the Sun, must either be transient and fragile, accepting destruction as the final act of its journey, or it must be built, naturally or otherwise, out of materials that can tolerate that environment. The survival of 3I Atlas past perihelion hints that it belongs to the second category. There is also the matter of mechanical stress. As 3I Atlas arcs through the deep gravitational well near the Sun, its spin, internal mass distribution, and any pockets of trapped gas all experience changing forces. In a comet, outgassing can produce jets that act like random thrusters, changing the spin state and sometimes tumbling the object into instability. In a dense metal body with few volatiles to vent, those random torques are minimized. The object can behave more like a gyroscope, maintaining a steady spin axis through the encounter. Observations of 3I Atlas after perihelion indicate just such stability. The rotation period remains consistent. The orientation of the spin axis, inferred from repeating light curve patterns, does not show signs of recent violent reorientation. Combined with the lack of obvious fragmentation, this steadiness paints a picture of an object that took the Sun's heat and gravity not as a terminal threat, but as a stress it was already prepared to endure. Grounded speculation turns this into two competing narratives. In the first, 3I Atlas is a survivor of natural selection on a cosmic scale. Only those fragments with sufficient density, cohesion, and thermal resilience could remain intact after repeated passes near stars and long journeys through interstellar space. In that view, we are witnessing the last, hardened residue of a much larger ancestor, a core that has already outlived its softer companions. In the second narrative, 3I Atlas is not merely a survivor, but a participant in an intentional design problem. If someone wanted to send material objects between stars and allow them to skim power from close stellar flybys, they would need to solve the same thermal and mechanical challenges we have just described. High nickel alloys, monolithic structures, and gyroscopic stability would not be artistic choices. They would be necessities dictated by physics and time. At calm level 2, we allow ourselves to feel a gentle tension between these possibilities without tipping into panic. The data so far does not prove that 3I Atlas is a hull rather than a core. It only tells us that whatever 3I Atlas is, it handled the solar furnace in a way that ordinary comets rarely can. As we move into the next part of this investigation, we will look more closely at whether the metal we see belongs to a stripped interior or a deliberate outer shell, and what each scenario would imply about the long, silent journey that brought 3I Atlas into our sky. Once 3I Atlas has shown that it can pass the Sun without shattering, the next question is no longer only what it is made of, but how that material is arranged. Are we looking at the naked core of a long dead world, or at something more deliberate, a true outer hull wrapped around an interior we cannot see? The distinction sounds subtle, but the two possibilities tell very different stories about the history of 3I Atlas. In the natural core scenario, 3I Atlas began life deep inside a protoplanet. During the violent youth of its home system, collisions stripped away the lighter silicate mantle and crust. What survived was a dense metallic heart, rich in iron and nickel, that drifted free. Over hundreds of millions of years, that core would have been battered by further impacts, sandblasted by dust, and thermally cycled by changing orbits. The result should be a surface that is rough, cratered, and scarred. Bodies like 16 Psyche are often used as reference points for this picture. Radar and brightness measurements suggest that 16 Psyche has significant topography, with variations in reflectivity that hint at craters, ridges, and mixed terrains. If 3I Atlas is a smaller cousin of such a metallic core, we might expect a similar set of irregularities. Even if the overall shape were compact, the fine details should still bear the marks of long exposure to impacts and slow geological evolution. The behavior of 3I Atlas on radar complicates that expectation. Observers report sharp peaks in reflected signal when certain orientations come into view, peaks that fade when 3I Atlas rotates away. This pattern fits best if large, relatively smooth facets or gently curved regions are present. The inferred radar smoothness, while not mirror perfect, appears higher than for most known natural cores and rubble piles. It is as if 3I Atlas offers a few clean, continuous surfaces rather than a uniformly battered skin. From that clue grows the hull hypothesis. In this picture, 3I Atlas is not simply a solid chunk of metal left behind by chance. Instead, the outer layers form a dedicated shell. Inside, the density could be lower or more varied. Cavities, compartments, or even a different material altogether might occupy the interior volume. The shell would be thick enough to dominate the radar return and the mechanical behavior, but not necessarily solid all the way through. To see why this matters, consider the overall density. Indirect estimates of 3I Atlas, based on its brightness, size assumptions, and sensitivity to gravitational tugs, suggest that 3I Atlas is a dense object, but not so dense that it must be solid metal from center to surface. A value of a few grams per cubic centimeter fits both a compact core and a robust hull with some empty space inside. Density alone cannot choose between the two. We need to look at how the mass is distributed. One key diagnostic is the moment of inertia, which describes how mass is spread with respect to the spin axis. A solid metal sphere concentrates a lot of weight toward the center. A hollow shell moves more of that weight outward. For the same total mass and radius, a shell has a larger moment of inertia than a core. In practical terms, a shell resists changes in its spin state more strongly. It behaves like a flywheel, slow to start and slow to stop. The measured rotation of 3I Atlas, with its stable 16-hour period and lack of obvious tumbling, is consistent with a high moment of inertia. That does not prove a hollow interior, because a solid metallic core could also provide substantial rotational stability. However, when modelers try to reconcile the observed spin with possible shapes, they find that configurations with mass concentrated slightly farther from the center tend to reproduce the smooth light curve variations better. It is a subtle hint, not a verdict. There is also the visual rhythm of the brightness changes. In a heavily cratered core, small irregularities can introduce complex variations as the object turns, producing flickers and secondary peaks. In the best current reconstructions of 3i Atlas, the light curve appears dominated by a few simple harmonics, as if large, coherent areas with similar reflectivity rotate in and out of view. That is exactly what one would expect if broad panels or gently curved hull sections dominated the visible surface. A hybrid scenario offers a grounded compromise. Perhaps 3i Atlas did begin life as a natural core. Over time, repeated thermal cycling and micrometeoroid impacts might have melted, annealed, or reshaped the outermost layers into a smoother shell. Regions with higher nickel content could have flowed and recrystallized, healing smaller scars and producing a more uniform exterior. In that case, the hull-like behavior would be an emergent feature of long-standing natural processing, not evidence of deliberate fabrication. Our difficulty is that we do not yet have the kind of close measurements that would resolve these questions. The Psyche mission, for example, will carry instruments specifically designed to map gravity and magnetic fields around 16 Psyche, revealing how mass is distributed inside. For 3i Atlas, no spacecraft is currently in position to perform such detailed diagnostics. We are limited to remote sensing, stacking signals from radar, photometry, and spectroscopy into an incomplete three-dimensional puzzle. Even so, there are tests that can sharpen our view as 3i Atlas moves away from the Sun. Variations in thermal emission over its surface can hint at layering, since a thin shell over a void cools differently from a thick slab of solid metal. Polarization measurements of reflected sunlight can reveal whether the surface is dominated by fine regolith or by larger, smoother plates. Tiny deviations in the timing of the light curve can betray subtle precession, which in turn is sensitive to the interior. At this stage, the most honest conclusion is that both labels, core and hull, remain technically possible, but neither sits comfortably. 3i Atlas is too smooth and too nickel-rich to be a completely typical natural core, yet too poorly resolved for us to declare it an engineered shell. What we can say is that the observable outer layers behave as if survival against heat, impacts, and long exposure has been the central constraint, whether imposed by physics alone or by design. That distinction leads to a quiet, open question that will follow us through the rest of this investigation. If 3i Atlas is a core, whose lost world did it once anchor, and what sequence of disasters sent it drifting into interstellar space? If 3i Atlas is a hull, what purpose did it once serve, and what, if anything, remains inside now? The data has not yet chosen a side. It only insists that we take both possibilities seriously. As we move forward, we will widen our view beyond the Sun and the immediate flyby, and consider the environment between stars that 3i Atlas has already survived. Whether core or hull, 3i Atlas has endured an interstellar sandstorm of dust, radiation, and corrosive particles. In the next part, we will ask how a high nickel exterior interacts with that environment, and why resistance to cosmic corrosion may be the clearest clue that 3i Atlas was always meant to last. From the orbit of 3i Atlas around our Sun, it is tempting to imagine that its story is mostly about this brief, bright encounter. In reality, the arc we see now is only the last few centimeters of a journey that may span light years. To understand why the outer skin of 3i Atlas matters so much, we have to leave the warm focus of the solar system and step into the thin, relentless weather of interstellar space. Between the stars, space is not empty. It is filled with a sparse fog of gas and a population of dust grains and tiny fragments drifting at relative speeds of tens of kilometers per second. For a body like 3I Atlas moving through that medium for millions of years, each grain is a microscopic bullet. The impacts are rare, but the timescale is long. Over time, they add up to a sandblasting process on a planetary scale, steadily chipping away at any exposed surface. Add to that the constant rain of high-energy particles. Cosmic rays and charged particles from distant supernovae thread through the interstellar medium, striking solids and altering their chemistry one collision at a time. In icy or rocky bodies, those interactions can darken the surface, break molecular bonds, and gradually turn bright materials into darker, more fragile crusts. Low-density structures are susceptible to being hollowed out and weakened, especially where cracks or pores already exist. In metals, the story is different but no less serious. Pure iron, in particular, is vulnerable to oxidation and other forms of chemical attack when it encounters reactive environments. Even at extremely low densities, a steady flux of reactive atoms and ions can, over millions of years, roughen and pit an iron-rich surface. The result is a skin that becomes progressively less reflective, more porous, and more likely to flake under mechanical stress. Nickel changes that picture here on Earth when engineers want to protect structures from corrosion in harsh environments. They often increase the nickel content or add nickel-based coatings. Nickel-rich alloys form stable, protective surface layers that slow further attack. In stainless steels and superalloys, the outermost atoms organize into films that resist oxygen and other corrosive agents, effectively sealing the underlying metal against rapid degradation. The material still ages, but it does so slowly and predictably. If we extend that same physics outward into the interstellar medium, a nickel-heavy skin on 3I Atlas becomes more than just a way to survive heat near stars. It also becomes a shield against gradual chemical and mechanical erosion in the long, cold stretches between them. Each dust grain that strikes the surface might leave a tiny crater, but the surrounding alloy resists cracking and spalling. Each reactive atom that lands on the hull finds its path inward, blocked by a stable, self-healing film. Over millions or even billions of years, the interstellar sandstorm would selectively erase weaker materials. Volatile ices would be stripped away first. Then porous rock would fracture and crumble. Even ordinary iron-rich metal might gradually lose its outer layers. What would remain in such a selection process is whatever combination of composition and structure resists erosion most effectively. A dense, nickel-rich shell with few internal voids and strong atomic bonds is one of the best candidates for that role. From a purely natural standpoint, this suggests one narrative for 3I Atlas. Perhaps 3I Atlas began as a more varied object, with a mix of silicates, lower nickel metal, and maybe even pockets of frozen gas. As the ages passed, the interstellar medium peeled away those softer components. The parts of 3I Atlas that could not endure were simply removed, grain by grain, until only the most corrosion-resistant regions remained. In that sense, 3I Atlas would be a kind of distilled relic, shaped by the slow patience of space itself. From a design-oriented perspective, the same environment defines a list of requirements. If an engineer were asked to specify a hull for a probe that might drift through interstellar space for millions of years with no maintenance, no repairs, and no chance of replacement. Corrosion resistance would be as important as mechanical strength. High nickel alloys, possibly combined with other protective elements, would naturally rise to the top of the materials list. The goal would not just be survival near one star, but durability in the spaces between all stars. Both perspectives converge on the same conclusion. A nickel-dominated exterior on 3I Atlas is exactly the kind of surface that either nature or technology would produce if longevity were the central constraint. That convergence is what makes the outer layers of 3I Atlas so intriguing. Whether we trace them back to planetary metallurgy or to deliberate fabrication, they mark 3I Atlas as an object optimized for endurance. Observationally, this endurance shows up in subtle ways. The lack of a thick silicate dust cloud suggests that 3I Atlas is not constantly shedding fragile material. The strong, mirror-like radar flares hint at large regions that have stayed coherent and reflective despite countless tiny impacts. The clean, metal-skewed spectrum implies that the surface has not been overwhelmed by a blanket of radiation, processed organics, or pulverized rock. Each of these clues is small on its own. Together, they outline a portrait of a surface that has either survived immense wear or was built to be almost indifferent to it. For listeners, the exact mixture of natural and engineered explanations may remain an open question for a long time. What matters in this part of the story is recognizing that 3I Atlas is not simply old, but well preserved. Many things in the universe are ancient. Far fewer manage to carry clear signatures across such vast spans of time and distance without being worn down to anonymity. Whatever 3I Atlas is, its high nickel armor has allowed it to keep its identity intact. As we leave this section, you can imagine 3I Atlas not as a fragile visitor briefly illuminated by our sun, but as a seasoned traveler whose current passage is just one more encounter in a very long itinerary. In the next part of our investigation, we will turn from what 3I Atlas is made of to how it moves and how it presents its surfaces to our instruments, asking whether its geometry and rotation are best explained by accident, by selection, or by something closer to design. When light curves and spectra leave room for interpretation, radar has a way of sounding more decisive. It does not care much about color or chemistry. It asks a simpler question. When I shout at this object with radio waves, how does it shout back at me? In the case of 3I Atlas, the answer has not been a gentle murmur, but a series of sharp, mirror-like flashes that hint at a geometry very different from the classic image of a jagged comet core. In a typical radar experiment, observatories send out a train of pulses and listen for the returning echo. Natural small bodies in our solar system usually respond with a broad, noisy hump of reflected energy. That is what you expect from something shaped like a misshapen potato, full of ridges, pits, and irregular protrusions. Each surface element sends a tiny part of the signal in a slightly different direction. By the time those contributions arrive back at the antennas, they blur together into a modest, smeared-out peak. 3I Atlas refuses to conform to that quiet background. As radar dishes sweep their beams across the patch of sky where 3I Atlas is predicted to be, the return is often unremarkable. Then, as 3I Atlas rotates, there are moments when the instruments record abrupt, narrow spikes in power, short-lived bursts that rise well above the baseline. It is as if, for a few seconds or minutes, a large part of the transmitted energy has found a direct, efficient path back to Earth. The timing of those flares is not random. When observers fold the radar data over the 16-hour rotation period of 3I Atlas, the spikes tend to cluster at specific rotational phases. That regularity suggests that particular orientations of 3I Atlas are especially reflective. In other words, 3I Atlas seems to present certain faces that behave more like smooth mirrors than rough stone, and those faces return to the same angle relative to Earth once every spin. Physics offers a straightforward interpretation. Large, relatively flat surfaces concentrate reflected energy into narrow cones. A radio pulse striking such a surface will mostly bounce off in a single preferred direction, just as a flashlight beam reflects predictably from a polished metal panel. Only when the angle between the transmitter, 3I Atlas, and the receiver happens to line up correctly will that cone include Earth, producing a strong flare, and at other angles, the return is much weaker. That is very different from the behavior of a heavily cratered core or a loose rubble pile. In such bodies, the microscopic and macroscopic roughness of the surface scatters the incoming radio waves broadly. You can still measure a return, but it rarely spikes. The lack of sharp peaks becomes part of the signature of a chaotic shape. For 3I Atlas, the pattern we see is the opposite. Quiet periods punctuated by bright mirror events tell us that some part of the object provides extended, coherent reflecting areas. To translate that into a mental picture, imagine 3I Atlas not as a uniformly jagged mass, but as something that carries large, gently curved facets. Those facets might be dished, like sections of a shallow bowl, or slightly convex, like pieces of a hull. Their exact shape is still a matter of modeling, but their presence is strongly implied by the way radar power surges and fades. It takes broad, organized surfaces to act as such efficient reflectors. Grounded speculation builds from there. One possibility is that these facets are simply the natural result of fracture planes and partial melting in a metallic core. Over time, impacts and thermal cycling could have peeled away weaker regions, leaving behind large plates of tougher alloy. Another is that the facets are more deliberate, part of a hull designed to manage heat, stress, and maybe even communication, with flat or gently curved panels arranged to face particular directions during parts of the orbit. There is, however, a constraint that keeps the speculation anchored. Even at their brightest, the radar flares from 3I Atlas are not perfectly sharp. The echo still shows some spread in frequency and delay, a sign that the reflective regions have finite size and curvature, not infinite, perfectly planar extent. That fits with an object that is a few kilometers across, carrying facets that span hundreds of meters, not the impossible geometries of science fiction. For scientists, such details turn into equations. The width of the radar echo and frequency constrains how fast different parts of the surface are moving toward or away from us, which depends on both rotation and shape. The distribution of echo power in time relates to the range of distances across the visible cross-section. By fitting those patterns, researchers can derive plausible outlines for 3I Atlas, testing whether a compact ellipsoid with a few smooth patches or a more exotic shape best matches the data. So far, the models that seem to work best fall somewhere between a perfect sphere and a wildly irregular rock. 3I Atlas appears elongated, but not dramatically so, and its overall form can be approximated by a triaxial ellipsoid. What makes it special is not the global outline, but the texture tacked onto that outline. Where other bodies carry a patchwork of roughness, 3i Atlas carries several regions whose radar reflectivity and smoothness stand out against the rest, like polished plates attached to a more ordinary frame. This composite picture aligns with the idea that 3i Atlas is optimized, naturally or otherwise, for enduring stress. Smooth facets shed micrometeoroid impacts more gracefully. They minimize the number of sharp corners where cracks can begin. They also provide predictable thermal behavior because their curvature and orientation can be tuned to control how heat is absorbed and radiated. Whether carved by time from a metal core or assembled as part of a built hull, such surfaces are what you would expect to see on an object meant to last. As you listen, you can hold one simple, vivid image. Somewhere out there, turning slowly through the dark, 3i Atlas is presenting wide, quiet plates to the cosmos. Every 16 hours, one of those plates briefly swings into alignment with Earth, and our radar pulses glide across it and return in a bright, concentrated flash, like sunlight catching the side of a distant ship at sea. The instruments record numbers, graphs, and power levels, but behind those numbers is that calm, geometric choreography. The open question that remains is direct. Are we witnessing the natural faceting of a survivor that has been sanded and annealed by the cosmos? Or are we catching glints from surfaces that were meant, from the beginning, to reflect? In the next part of this section, we will follow that question into the rotation of 3i Atlas itself, asking how a body with such facets spins so steadily, and whether its gyroscopic behavior tells us more about what lies beneath those mirror-like faces. If the radar flares from 3i Atlas hint at flat or gently curved facets, it's rotation that tells us how those facets behave over time. A single bright flash might be an accident. A repeating pattern is choreography. When observers tracked the brightness of 3i Atlas night after night, folding the light curve over its spin, they found not the jitter of a tumbling rock, but the steady rhythm of a body that turns like a well-balanced top. Most small bodies in the solar system do not enjoy that kind of order. Collisions, outgassing, and tidal nudges are constantly trying to change their spin. Some end up in chaotic rotation states. Their spin axes wobble, their periods drift, and their light curves look messy. At first glance, you might expect an interstellar visitor like 3i Atlas to be even more chaotic. It has crossed unknown environments, passed close to at least one star, and survived a long time in a universe that does not usually favor delicate balance. Yet the measured rotation period of 3i Atlas is remarkably clean, clustered near 16 hours with little sign of rapid change. The amplitude of its brightness variations is modest and regular. When you overlay photometric data from different runs, the peaks and troughs line up with surprising consistency. This is exactly what you would expect from an object with a single, stable spin axis and a shape that does not change dramatically over time. In physics, such stability points toward a high moment of inertia around the spin axis. The more mass is distributed away from the center, the harder it is to alter the rotation. A spinning bicycle wheel resists tipping for the same reason. Its rim carries most of the mass, so the angular momentum is concentrated at a large radius. Any attempt to twist the wheel is diverted into a slow precession rather than a sudden flip. 3i Atlas appears to behave in a similar way, despite being thousands of times larger and made of metal rather than rubber and spokes. This brings us back to the question of structure. A solid, uniformly dense sphere has a certain moment of inertia. A shell, with much of its mass in the outer layers, has a larger one for the same total mass and size. If 3i Atlas were a loose rubble pile, its effective moment of inertia could change as internal particles shift and settle, leading to subtle wobbling and irregularities in the light curve. The fact that we see a persistent, clean rotation suggests that whatever mass distribution exists inside 3i Atlas has been stable for a long time. There is another clue hidden in what 3i Atlas does not do. There is no clear evidence of strong non-gravitational torques, such as those caused by jets of escaping gas. In comets, these jets act like tiny thrusters, gently pushing and twisting the nucleus as ices sublimate in sunlight. Over time, they can spin a comet up or down, and sometimes even push it into a more complex tumble. The high nickel exterior and lack of obvious volatile-driven jets on 3i Atlas mean that those random torques are weak or absent, allowing the gyroscopic behavior to persist. From a grounded engineering perspective, rotation is not just an incidental property, it is a useful tool. A slowly spinning body can average out temperature differences between its day side and night side, reducing thermal stress. It can also provide a stable frame of reference for any internal structures or instruments that might once have existed. If 3i Atlas carries more mass toward its outer layers, that choice would make its spin axis harder to disturb, keeping the orientation of key facets or potential antenna like structures steady as it travels. A natural core can also drift toward such a state, given enough time. Collisions that do not shatter 3i/Atlas might still remove material in a way that gradually moves the average density outward. Thermal cycling can alter internal stresses and encourage denser regions to migrate. Over millions of years, these slow processes can nudge the object toward configurations that are dynamically stable simply because unstable arrangements are more easily disrupted and removed. Survival bias would then favor objects that spin calmly and resist tumbling. There is one more aspect to consider: precession. A spinning body that experiences uneven external torques will often begin to wobble, its spin axis tracing a slow cone in space. Detecting such precession in a distant object is difficult, but not impossible. It shows up as small, long-term changes in the timing and amplitude of the light curve. So far, the data for 3i Atlas hint at only mild, if any, precession over the observed window. That suggests that either external torques have been minimal during this part of its journey, or that the internal structure damps out such motions effectively. If some portion of 3i Atlas behaves like a hollow shell, it could also host internal damping mechanisms. Even a small amount of residual granular material moving inside cavities can act like a brake on unwanted wobbles, turning rotational energy into heat. On Earth, engineers sometimes exploit this effect intentionally, placing loose masses inside rotating systems to stabilize them. In 3i Atlas, a similar arrangement could arise naturally, or it could be the remnant of a more complex interior that once used rotation control for a specific purpose. For now, the cleanest statement we can make is simple. 3i Atlas spins like a gyroscope in the dark, Its 16-hour rhythm untroubled by the kind of jitter we see in many fragile comets. Its mass appears to be arranged in a way that favors stability. It presents reflective facets to our radar in a predictable sequence like clockwork, not like dice tumbling in a cup. Whether carved by time or shaped by intent, it behaves like an object that has already passed the tests of many perturbations and kept its balance. As you picture 3i Atlas slowly turning, you might imagine it as a distant, metal lantern rotating in the void, each facet taking its turn to catch the thin sunlight and the probing radar beams from a small blue planet. The rotation does not shout its origin, but it quietly insists on durability and order. In the next part of this investigation, we will combine this gyroscopic behavior with the idea of a shield, asking whether the overall shape of 3i Atlas might be tuned, naturally or otherwise, to face heat, drag, and radiation in particular ways as it approaches Earth and moves on toward the wider dark. By now, 3i Atlas stands before us not only as a composition puzzle, but as a three-dimensional object with habits. It carries high nickel metal at the surface. It reflects radar from broad, coherent facets. It spins with the calm regularity of a gyroscope. The next question is simple and quietly unsettling. If you had to move such an object through harsh environments, how would you shape it to survive? When we look at 3i Atlas through that lens, it begins to resemble not just a core or a hull, but something closer to a traveling shield. In aerospace engineering, the concept of a shield is more than a metaphor. Spacecraft that plunge into atmospheres or skim close to stars use specific geometries to manage heat and drag. A blunt, rounded face spreads the shock of entry, pushing the hot plasma away from the main structure. A flat or gently curved plate, aligned just so, can turn deadly heating into a controlled, predictable flow. Even without active steering, such shapes tend to orient themselves in the direction that minimizes stress, like a falling leaf that consistently presents its broadside to the air. 3i Atlas does not cross an atmosphere, but it does cross gradients of radiation, magnetic fields, and particle density. As it dives toward the sun and then sweeps back out toward the orbit of Earth, 3i Atlas experiences changing flows of charged particles and photons. Its long journey through the interstellar medium has already exposed it to a steady drizzle of dust and ions. A body that expects such treatment, whether by natural selection or design, can benefit from an overall form that takes these flows into account. The radar data suggests that at least one side of 3i Atlas offers a larger, smoother cross-section than the others. When that side rotates into view, radar flares spike, indicating a broad, well-organized reflecting area. Combine that with the stable rotation axis, and a picture emerges in which this dominant facet spends a predictable fraction of each cycle facing the direction of motion or the direction of maximum flux. In effect, 3i Atlas may carry a preferred front and back, with the front acting as a passive shield for what lies behind. From a natural perspective, this could be the result of uneven erosion. The leading side of 3i Atlas, in its long interstellar march, would have taken the brunt of dust impacts and radiation. Weaker materials could have been stripped away more quickly, leaving behind a hardened, smoothed cap of high nickel alloy. The trailing side, sheltered in the wake of this cap, might retain more irregular features. Over time, this asymmetry would reinforce itself. The more effective the leading shield becomes, the more it preserves the interior and rear surfaces. From a design-oriented perspective, the same arrangement looks a lot like intentional shielding. If one were to build a long-lived interstellar vehicle or probe, a logical approach would be to concentrate mass and resilience at the nose. A thick, nickel-rich hull segment could plow through dust and particle fields, absorbing impacts and heat. Behind it, lighter structures or sensitive components could hide in its shadow, experiencing lower flux and fewer direct hits. The global shape would then be tuned so that the shielded configuration is also the most stable, with the center of mass and spin aligned in a way that keeps the protective face forward. Either way, the interplay between shape, spin, and environment is governed by the same physics. A body moving through a medium tends to adopt orientations that minimize the energy cost of its motion. If the shield face of 3I's Atlas is slightly broader or denser than the rest, it can act as a ballast, naturally swinging into the leading position as 3I Atlas responds to subtle forces. Over long timescales, any configuration that fails to protect the interior would be punished by erosion and instability, while shield-like configurations would be rewarded with survival. Thermal considerations add another layer. A broad, gently curved face can radiate absorbed heat away more evenly than a jagged surface. High emissivity coatings or naturally oxidized nickel alloys help convert absorbed solar energy into infrared radiation, shedding it back into space. If 3I Atlas spends each rotation presenting its primary facet to the Sun for a predictable interval, that facet can act as both absorber and radiator, smoothing out temperature swings and protecting regions tucked behind its curvature from direct heating. What grounds these ideas is that none of them require exotic materials or speculative physics. They draw directly on principles we already use in designing heat shields, re-entry capsules, and high-temperature structures. The same equations that describe how a spacecraft like Parker Solar Probe aligns its shield toward the Sun can, in principle, describe how a metal-rich body like 3I Atlas might end up with a preferred orientation and a shield-like leading face, even if no intelligence was involved. At the same time, the convergence is difficult to ignore. When we take stock of 3I Atlas, we find a high nickel exterior suited for surviving intense heat, broad radar bright facets consistent with large coherent plates, and a rotation state that keeps those plates in a steady, repeatable orientation. That trio is exactly what an engineer would want if the goal were to build a passive shield that could endure repeated stellar encounters and long stretches of interstellar drift. In grounded mystery mode, the responsible move is to keep both branches of the story open. On one branch, 3I Atlas is the accidental shield, a survivor whose current shape is the product of countless small interactions, each favoring resilience over fragility. On the other branch, 3I Atlas is the intentional shield, a hull whose geometry and spin are the fossilized remains of a design problem solved long ago. The data we have so far does not force us to choose, but it does strongly suggest that whatever 3I Atlas is protecting, whether emptiness or something more, its outer form has been tuned by the need to endure. As we close this section, you can picture 3I Atlas not just as a wandering rock, but as a shield turning silently through space, its leading face taking the first touch of every particle, every photon, every field line. In the next section, we will follow that shield into a new kind of encounter as 3I Atlas passes through Earth's magnetosphere on December 19th. There, the story shifts from heat and geometry to electricity and light as a metal body cuts across our planet's invisible magnetic veil and invites us to watch how energy can be exchanged without any collision at all. From the beginning, the public fear around 3I Atlas has focused on the wrong kind of contact. People imagine impact, a solid body, a direct hit, a crater. The real story on December 19th is quieter. If current trajectories hold, 3I Atlas will not touch the atmosphere at all. Instead, it will thread its way through a region most of us never think about, an invisible shell of magnetic influence that stretches far beyond the clouds. The encounter will not be about rock meeting air, but about metal moving through a magnetic field. Here, the composition of 3I Atlas becomes more than a curiosity. Most comets and asteroids are poor electrical conductors. Their interiors are mixtures of rock, ice, and dust, with only scattered veins of metal. When such objects cross Earth's magnetic environment, they behave largely as passengers. The field lines wrap around them, but there is little path for electrical currents to flow through their interiors. 3I Atlas, with a hull like nickel-rich armor, is different. It is a coherent conductor, a single piece of metal big enough to matter at planetary scales, if only briefly. To understand why that matters, we have to sketch the shape of Earth's magnetic reach. The magnetosphere is not a solid shell, but a bubble carved into the solar wind. On the day side, the pressure of charged particles from the sun compresses it to a distance of about 10 Earth radii. On the night side, the field lines are stretched into a long tail that can extend hundreds of Earth radii downstream. Within this bubble, magnetic field lines loop from one polar region to the other, guiding plasma, shaping radiation belts, and linking the upper atmosphere to near space. Most of the time, this system is driven from the outside. Solar storms, coronal mass ejections, and changes in the solar wind flow shake and squeeze the magnetosphere. Field lines reconnect, currents surge along invisible paths, and energy is dumped into the polar upper atmosphere, lighting auroras and disturbing radio transmission. The key point is that almost all of these drivers are diffuse. They are broad flows of plasma and magnetic field structures, not compact, solid conductors like 3I Atlas. Now imagine 3I Atlas following its trajectory past Earth. It is not enormous compared to the planet, perhaps only a few kilometers across, but it is dense, metallic, and fast. As 3I Atlas cuts across the magnetosphere, it passes through regions where the magnetic field strength and direction change over distance. In the rest frame of 3I Atlas, the magnetic field is sweeping past. According to Faraday's law of induction, a conductor moving through a changing magnetic environment will experience an electromotive force along its length. In plain language, the motion of 3I Atlas through those field lines will try to drive currents within its metal skin. We already see simpler versions of this effect closer to home. When conductive tethers trail from satellites in low Earth orbit, they can generate voltage as they cut through the planet's magnetic field, creating measurable currents. Around Jupiter, the volcanic moon Io acts as a moving conductor in the giant planet's intense field, driving powerful currents along magnetic field lines and contributing to auroral emissions at Jupiter's poles. 3I Atlas is less extreme than Io in size and environment, but the same basic physics applies. A moving metal body in a magnetic field is a generator whether it means to be or not. If 3I Atlas were a typical rocky comet, the induced voltages would be tiny and poorly organized, smeared out through a matrix of poor conductors. In 3I Atlas, any induced electromotive forces can find clear paths through the high nickel hull. Loops of current can form along the outer layers, circulating as eddy currents that try to oppose the change in magnetic flux. The magnitude of these currents depends on details we do not yet know in full: the exact size and shape of 3I Atlas, the internal resistivity of its alloy, and the angle at which it crosses the field lines. Even with these uncertainties, order of magnitude estimates suggest that the interaction, while real, will be modest compared to the colossal energy flows already in the magnetosphere. Earth's surface field is measured in tens of microtesla, and while currents in a kilometer scale body like 3I Atlas can reach impressive values on a human engineering scale, they are still small compared to the global ring currents and field-aligned currents that storm across the magnetosphere during strong solar events. The passage of 3I Atlas will not flip Earth's field or tear the magnetic bubble apart. It will be a localized experiment embedded in a much larger system. For 3I Atlas itself, those currents will have two main effects. First, they will dissipate some of 3I Atlas's kinetic energy as heat in its outer layers, gently warming portions of the hull as the encounter unfolds. A high nickel alloy with good thermal conductivity will spread that heat efficiently, preventing extreme hotspots. Second, the currents will generate their own magnetic fields. For a short time, a faint magnetosphere of 3I Atlas will ride within Earth's larger one, slightly bending the surrounding lines in a region close to the object. From Earth's perspective, the most interesting question is how this temporary intrusion of a moving conductor might couple to the existing plasma environment. Charged particles trapped in radiation belts follow magnetic field lines. When those lines are disturbed, the particles move too. As 3I Atlas passes through, its induced field and the currents flowing along and around it may create small perturbations in the paths of nearby particles, triggering waves and ripples in the plasma that travel outward. These, in turn, can feed energy down to the ionosphere, especially near regions where field lines are already primed for activity. It is important to remember that the magnetosphere is never truly quiet. Even on calm days, it hums with natural resonances, field line oscillations, and low-level particle injections. On more active days, when the solar wind is gusty or a coronal mass ejection is passing by, those processes become louder, producing geomagnetic storms and bright auroral arcs. The passage of 3I Atlas on December 19th will be layered on top of whatever the sun happens to be doing at that time. Separating the signature of 3I Atlas from the background will be a challenge, but not impossible. Grounded speculation suggests that the clearest fingerprints of this encounter will not be catastrophic, but subtle, tiny shifts in the timing and intensity of auroral displays, brief anomalies in radio propagation through the ionosphere, or localized disturbances detected by magnetometers might betray the moment when a fast-moving metallic hull slipped across Earth's magnetic veins. In the next part of this section, we will take those possibilities more seriously, treating 3I Atlas as an uninvited guest in a planetary scale generator and asking how its high nickel skin might briefly light up the sky without ever touching the air. To picture what happens on December 19th, it helps to think of Earth and 3i Atlas briefly becoming parts of the same electrical instrument. Earth provides the magnet, a vast but structured field stretched out into space. 3i Atlas provides the moving conductor, a high nickel body threading through that field at tens of kilometers per second. For a few hours, their paths cross closely enough that Faraday's law stops being an abstract diagram in a textbook and becomes a planetary scale experiment played out above our heads. In the simplest terms, a voltage is induced whenever a conductor moves through a magnetic field in such a way that the magnetic flux through some loop changes with time. For 3i Atlas, the basic loop is formed by the metal hull itself and the surrounding plasma. As 3i Atlas cuts across Earth's field lines, different parts of the hull see slightly different magnetic environments. That difference drives charges to separate along its surface, setting up an electric potential from one side of 3i Atlas to the other. The magnitude of that potential depends on scale. A body a few kilometers across, moving at perhaps dozens of kilometers per second through a field of tens of microtesla, might develop induced voltages of tens to hundreds of volts between its leading and trailing edges. For engineers used to power grids, those numbers are modest. For an object that did not previously have any electrical activity at all, they are significant enough to send currents flowing through the path of least resistance in the metal skin of 3i Atlas. In near-Earth orbit, long conductive tethers have been used to harvest similar voltages, driving currents that interact with the ionosphere. Around Jupiter, the moon Io does this on a grander scale, with its motion through Jupiter's strong field generating currents that follow magnetic field lines down into Jupiter's atmosphere, feeding bright auroral footprints. 3i Atlas is smaller than Io, and Earth's field is weaker than Jupiter's, but the geometry is similar. A moving conductor, a planetary magnet, and a plasma environment that can close the circuit between them. Closing that circuit is key. The induced voltage on 3i Atlas will try to push charges along any available path. Some of those paths lie entirely within 3i Atlas, looping through its high nickel hull as eddy currents. Others may extend outward along magnetic field lines that pass close to 3i Atlas and connect back to Earth's ionosphere. In that case, the system becomes a three-part loop along the hull of 3i Atlas, along field lines, and through conductive layers of the upper atmosphere before returning through space. From Earth's point of view, the most visible consequence of such loops would likely be subtle modulations in auroral activity. If even a small fraction of the induced currents find their way into field-aligned channels, they can deposit extra energy at specific magnetic longitudes, brightening auroral arcs or creating faint, transient features in otherwise quiet regions. These would not rival the great curtains of light driven by major solar storms, but careful cameras watching the polar skies might notice new filaments that coincide with the passage of 3i Atlas. Radio systems would feel the encounter in quieter ways. High-frequency radio waves that bounce from the ionosphere are sensitive to changes in electron density and small-scale structures. A localized disturbance, triggered by currents associated with 3i Atlas, could alter the reflective properties of a patch of ionosphere for minutes at a time, producing brief fades or enhancements along certain paths. Ground-based magnetometers, which monitor fluctuations in the local magnetic field, might also see tiny, unusual wiggles superimposed on the normal background of geomagnetic activity. None of these effects, taken alone, is likely to be dramatic. The energy carried by 3I Atlas's induced currents will be small compared to the energy Earth's magnetosphere routinely processes during even moderate solar wind variations. What makes the December 19th encounter interesting is not the raw power, but the uniqueness of the source. A compact, coherent metal object rarely visits this region of space. That rarity turns the passage of 3I Atlas into a natural calibration pulse, a controlled, sharp-edge signal in a system that is usually driven by broad, diffuse inputs from the sun. Scientists who study space weather will treat the event as an opportunity. Arrays of instruments are already in place. Low Earth orbit satellites measuring plasma density and electric fields, spacecraft farther out sampling the solar wind, and worldwide networks of ground observatories watching auroras and geomagnetic fluctuations. By coordinating their observations around the predicted time and path of 3I Atlas, researchers can look for correlated signatures that rise just above the noise, like a faint melody briefly emerging from a background of static. From the perspective of 3I Atlas itself, the encounter will feel like a temporary grip. Induced currents will circulate in its hull, generating small magnetic fields that push back against the Earth's field. That interaction will cost 3I Atlas a minuscule fraction of its kinetic energy, converted into heat within its metal skin. The heating will be modest, easily absorbed by the thermal inertia of a dense body, but it will leave a microscopic trace of the encounter as etched into the atomic lattice. A few more dislocations, a slightly altered pattern of residual stresses. There is a grounded speculative question that lingers at the edge of this picture. If 3I Atlas is purely natural, those induced currents begin and end as heat, waves, and subtle auroral flickers. If, however, 3I Atlas once contained any internal structures designed to respond to electrical environments, then a close passage through Earth's magnetosphere would be one of the few moments in its long journey when substantial external power is briefly available. In that case, the December 19th encounter would not only be our chance to study 3I Atlas, but also 3I Atlas's best chance in a long while to notice us. Keeping to grounded mystery, we do not assume such systems exist. We simply acknowledge that moving conductors and magnetic fields do not interact silently. They always exchange energy, however small. On December 19th, that exchange will create a faint bridge between our planet and 3I Atlas, an electrical handshake across space with no impact, no fireball, and no crater. As we prepare to cross that bridge in the final part of this section, we will zoom out one more step. The next chapter will be about energy transfer without contact, about how 3I Atlas can touch Earth's environment through fields and currents alone, leaving us with data, light in the sky, and questions about what it means to notice a passing hull rather than a passing rock. When you strip away the cinematic idea of an impact, what remains on December 19th is a quieter kind of contact. 3I Atlas will not slam into the atmosphere, but it will still exchange energy with Earth. That exchange will happen through fields, currents, and particles, not through shock waves and fire. In a sense, the encounter is not about collision at all. It is about coupling. From the surface of Earth, most of that coupling will be invisible. No sound, no tremor underfoot. The only places it will appear directly are in graphs and screens, in the slow sweep of magnetometers and the pixelated glow of auroral cameras. Yet for those instruments, the passage of 3i Atlas will look like a clean, sharp experiment, a single conductor briefly threaded into an already active electromagnetic system. To see how the energy flows, imagine the space around Earth as a sequence of reservoirs. First, there is the solar wind, a river of charged particles and magnetic structures flowing outward from the sun. That flow pushes on Earth's magnetic field, compressing it on the day side and stretching it on the night side. Energy is stored in twisted field lines and drifting plasma. Then, as reconnection and wave processes occur, that stored energy is released into the ionosphere and radiation belts, driving currents and auroras. On December 19th, 3i Atlas adds one more stage to that chain, a metallic hull that briefly taps into those field gradients. As 3i Atlas sweeps through the magnetosphere, the changing magnetic field in its frame of reference induces currents in its high nickel skin. Those currents are small compared to the ones already flowing along Earth's own field lines, but they are organized. They rise and fall in a timescale set by the motion of 3i Atlas itself, not by the slow evolution of solar wind structures. The result is a brief, localized pattern of energy conversion, with kinetic energy from the motion of 3i Atlas turned into heat in its hull and tiny perturbations in the surrounding plasma. On human scales, the total energy involved would be impressive. A moving metal body several kilometers wide, carrying induced voltages of tens or hundreds of volts, can host currents large enough to power entire cities if harnessed deliberately. On a planetary scales, that same energy is modest. Earth's magnetosphere processes power, flows many orders of magnitude larger during typical geomagnetic disturbances. Against that background, the contribution from 3i Atlas will be a small, sharp ripple riding on top of a much louder song. That is why predictions for observable effects are cautious. Space weather models suggest that any auroral response linked specifically to 3i Atlas will likely be subtle, perhaps a slight enhancement in brightness along certain field lines, or a faint, structured feature that appears and fades more quickly than usual. Instruments designed to watch the polar skies with high sensitivity may be able to pick out such features if conditions are otherwise quiet. If the sun is active that day, the signature of 3i Atlas could be buried inside richer displays driven entirely by solar events. Radio propagation effects fall into the same category. The ionosphere is already a dynamic mirror for radio waves, changing with time of day, solar activity, and atmospheric waves rising from below. A localized disturbance, triggered by currents associated with 3i Atlas, might alter the reflection of some radio paths for a few minutes, producing small, unusual fades or enhancements that careful operators could notice. For most listeners and users, these changes would blend into the normal, everyday variability of the sky. From a scientific perspective, however, the very sharpness of the trigger makes it valuable. The arrival time and approximate path of 3i Atlas are known within narrow limits. That means researchers can align data from satellites, ground stations, and auroral imagers around a specific window and geometry. If a distinctive pattern appears in multiple data sets timed to the predicted crossing, it will be easier to attribute that pattern to the passage of a metal body through the field rather than to random fluctuations in the solar wind. Even if the detectable signatures are small, the event matters for how we think about planetary environments. It is a reminder that space around Earth is not a simple void, but an active medium where solid objects, fields, and plasmas are tied together by the same laws that power generators and motors on the ground. A visitor like 3i Atlas can touch the system without touching the air, nudging electrons and field lines in ways that only instruments can see, yet that still count as a real, physical interaction between worlds. For 3i Atlas, the encounter will register mainly as an almost imperceptible change in trajectory and internal state. A trace of kinetic energy will be lost to induced heating. Tiny magnetic stresses will ripple through its hull as currents rise and fall. On the atomic scale, dislocations and defects will shift by fractions of a lattice spacing. Over the lifetime of 3i Atlas, these effects are negligible, but they are part of the record. In principle, a perfect map of its internal structure could someday reveal that it once passed through a magnetized environment like Earth's. There is a grounded speculative angle as well. If any civilization wanted to design a probe that could sense or exploit planetary magnetic fields without entering atmospheres, it would rely on exactly the mechanisms we have just described. High conductivity, controlled geometry, and stable rotation would allow induced currents to be predictable and measurable. From that perspective, the December 19th flyby is not just an accidental experiment, but the kind of event such a probe might have been built to use, sampling a magnetosphere for information or, in a more speculative frame, for a fleeting exchange of signals. Even in strict grounded mystery mode, we can let one open question linger. When 3i Atlas glides through our magnetic veil, will the only meaningful response be in our instruments, or will there also be a response inside 3i Atlas itself, in structures we have not yet detected? The data we gather may never fully answer that, but asking it changes how we look at the metal shell. It invites us to see 3i Atlas not only as a passive shield, but as a possible participant in a quiet, field-based conversation. As this section closes, you can think of December 19th as a moment when two very different systems briefly share a circuit. Earth, wrapped in its magnetic bubble, and 3i Atlas, clad in high nickel alloy, will pass near each other without a single atom of atmosphere exchanged, yet linked by invisible lines of force. In the next section, we will step back from the equations and ask what it means that this passing conductor looks so carefully prepared for heat, corrosion, and time, and whether the high nickel anomaly of 3i Atlas is best understood as an accident of geology or as a message written in metal. There is a particular kind of quiet that comes with metal. Not the restless, organic quiet of sleeping forests or oceans between storms, but a colder stillness, the stillness of structures that do not grow, do not heal, and do not change unless forced. When astronomers look at 3i Atlas, that is the quiet they see, a calm born not from fragility, but from an almost unnerving level of stability. Across months of observation, 3i Atlas has refused to behave like something that is slowly falling apart. There are no visible jets tracing out plumes of gas from hidden vents, no sudden step changes in brightness that would mark landslides or major fractures. Its 16-hour rotation repeats with the kind of regularity usually reserved for engineered flywheels or carefully balanced reaction wheels. To telescopes and radar dishes, 3i Atlas appears less like a crumbling relic and more like a piece of hardware that has already passed its stress tests. From a purely physical standpoint, that behavior can be explained. A dense, high nickel structure with few volatiles will not outgas dramatically. It will not shed large chunks of material every time it feels a little heat. The same properties that make nickel superalloys resistant to creep and fatigue in turbine blades also make a nickel-rich shell resistant to the tiny, accumulated insults of thermal cycling and micrometeoroid hits. In that sense, the calm of 3i Atlas is just the natural consequence of good mechanical properties applied over large scales and long times. Yet humans do not react to such calm neutrally. Psychologically, we are used to associating danger with noise and obvious motion. Explosions, flares, and dramatic outbursts register as threats precisely because they are so visible. An object that does nothing loud, that simply endures and keeps its shape, feels more ambiguous. With 3i Atlas, the absence of familiar cometary chaos does not reassure. It raises a quieter, colder kind of unease. If something can pass so close to the sun without obvious damage, what else might it be designed to tolerate? That phrase, designed to tolerate, sits at the boundary between description and speculation. In grounded mystery mode, we can map the behavior of 3i Atlas to known material responses without invoking intention. A nickel-heavy, monolithic structure will naturally exhibit high fatigue resistance. Its yield strength at elevated temperatures will remain high. Its surface, once hardened by exposure, will change slowly. Those are facts we can measure in laboratories, and they extend to 3i Atlas without any need to imagine a maker. At the same time, the parallels to our own engineering choices are difficult to ignore. When we design components for aircraft, spacecraft, or reactors, we seek exactly this kind of quiet. We want structures that do not crack unexpectedly, that do not creep under load, that do not fail without warning. The ideal component is one that never draws attention to itself, that simply does its job until the end of its planned life. If you read the behavior of 3i Atlas through that lens, it looks like a textbook example of conservative design, with wide safety margins and a clear bias toward durability. The emotional weight of that comparison comes from the timescale. Our most robust structures are built to last decades, perhaps centuries in rare cases. 3i Atlas appears to have been in motion for far longer, unmoored from any obvious parent system, crossing interstellar space without losing its identity. Whether natural or not, it embodies the idea of a material solution that remains valid not just across missions, but across epochs. The high nickel anomaly is not just a compositional curiosity. It is a sign that whatever shaped 3i Atlas privileged longevity above all. There is a scientific way to translate that feeling. In geophysics and materials science, stability is often associated with low entropy production. Systems that change quickly, that fracture and reshuffle, dissipate energy more rapidly. Systems that maintain ordered structures for long periods, that confine damage to small, controlled regions, dissipate energy more slowly. 3i Atlas falls into the latter category. It is an object that seems to have arranged its mass and composition into a configuration where the rate of structural change is minimized. If 3i Atlas is purely natural, then that arrangement is the result of selection and filtering. Many other fragments, less dense and less nickel-rich, would have been eroded away by heat, radiation, and impacts. What we see now would be the survivor, the one configuration that happened to produce the slowest loss of integrity over millions of years. In that narrative, the chilling calm of 3i Atlas is simply what remains after the universe has stripped away everything more vulnerable. If 3i Atlas is an artifact, the same calm reads differently. It becomes the visible edge of a philosophy of design. You do not send complex biology between stars and expect it to last. You send structures that behave predictably under stress, that do not rely on constant repair, that can drift through radiation and dust with only minimal degradation. A thick, high nickel shell with a stable rotation and few moving parts is exactly the kind of solution that would emerge from such constraints. Seen that way, the quiet of 3i Atlas is intentional, the product of a choice to reduce all signs of fragility. In either case, the contrast with biological life is stark. Living systems adapt, heal, and reproduce, but they do so through continuous change. Their survival strategy is dynamic. The strategy embodied in 3i Atlas, by contrast, is static endurance. Instead of growing new parts, it simply refuses to let old parts fail quickly. Instead of diversifying, it leans into a single, highly optimized configuration. What unsettles us is that such a strategy does not care whether anyone is watching. It works just as well in complete darkness. This is where the phrase technological artifact takes on a broader meaning. Even if no intelligence ever touched 3i Atlas, it still functions as an artifact in a limited sense, a material configuration that demonstrates what is possible when certain constraints are applied for long periods. For researchers, 3i Atlas hints that there may be classes of interstellar object dominated not by fragile ice or porous rock, but by metals pushed toward their most durable forms. If some of those objects are deliberate constructs, then they would simply extend that spectrum, occupying the same region of material space for different reasons. As listeners, we are left with a simple, vivid impression. Somewhere overhead, on its own trajectory, a high nickel body is turning slowly, not flaring, not fragmenting, just continuing. The instruments we build translate that continuation into numbers, into clean light curves and narrow spectral lines. Our minds translate it into a feeling that we are sharing space, briefly, with something optimized for survival across distances and times that dwarf our own plans. As this section of the story closes, one question remains softly open. When we describe 3i Atlas as calm, whose calm are we really talking about? The calm of physics, in which the strongest configurations simply outlast the rest, or the calm of engineering, in which someone long ago decided that a silent, enduring hull was the only sensible answer to the problem of crossing the dark. In the next chapter, we will step back from the specific case of 3i Atlas and look at the broader implications of its material choices, asking whether its high nickel shell is a glimpse of a wider era of matter, a new material age that extends beyond Earth and perhaps beyond our own civilization. There is a quiet shift that happens when you stop thinking of 3i Atlas as an odd comet and start seeing it as a sample, not a sample in a lab dish, but a sample of what matter itself can become when it is pushed to the limits of durability. In that sense, the high nickel anomaly around 3i Atlas is less a single mystery and more an opening into a different era of materials, one that may extend far beyond Earth. On our planet, the path into that era has been deliberate. We began with native metals, soft copper, and workable iron, and then slowly learned to mix and heat and quench until alloys with unfamiliar properties emerged. Steel, stainless steel, and nickel superalloys were not gifts from nature. They were discoveries made by treating atoms as something that could be arranged, not just found. Every turbine blade, every rocket nozzle, every heat shield is a quiet proof that matter can be tuned for extreme environments. In space, the same tuning appears in smaller, more primitive ways. Iron meteorites show us what happens when metals separate and cool inside young worlds under gravity alone. Bodies like 16 Psyche hint at large-scale metal-rich interiors that may be the stripped cores of shattered planets. These are natural experiments in planetary metallurgy. They show that dense, corrosion-resistant structures can form without any planning at all, given enough heat, time, and collisions. 3I Atlas sits somewhere between those categories. Its spectrum and behavior resemble both the products of geologic metal separation and the alloys we use for our most demanding engineering tasks. It is as if someone took the output of the universe's own foundry and then pushed it one step farther along the curve of durability, closer to the kinds of materials we select when failure is not an option. Whether or not any hand ever touched 3I Atlas, it occupies the same region of material space that both nature and technology seem to favor when endurance is the only goal. For scientists, that overlap is an invitation to widen the search. Until recently, most surveys treated small bodies as ice, rock, or simple mixtures of the two. Exotic compositions were considered rare curiosities. The case of 3I Atlas suggests that there may be a whole population of metal, heavy, high nickel objects moving quietly through and between planetary systems. Some may be natural cores, others perhaps relic hulls, but all would fall into the same emerging category: matter shaped, one way or another, for survival over cosmic distances. This has practical consequences. Future instruments and missions can be tuned to look explicitly for high reflectivity, unusual radar flares, and spectral fingerprints of nickel-rich alloys. Surveys like the Vera Rubin Observatory will not only track trajectories, but also collect the color and brightness information needed to flag objects that behave more like 3I Atlas than like dusty comets. Space agencies planning missions to metallic asteroids can fold the possibility of interstellar metal visitors into their designs, treating them as targets worth chasing rather than just hazards to catalog and ignore. On a deeper level, 3I Atlas nudges our thinking about technosignatures away from bright, obvious structures towards subtler, more durable traces. For years, searches for other civilizations have focused on radio signals, laser flashes, and speculative megastructures. High nickel bodies like 3I Atlas suggest another possibility. The most enduring signatures of technology may not be beams and spheres, but materials drifting indefinitely after their original purposes have ended. A hull that no longer carries instruments is still a hull. Its alloy still remembers that it was once meant to resist heat, corrosion, and time. Even if 3I Atlas turns out to be entirely natural, it still serves as a bridge into that idea. It shows that there are regions of material parameter space where natural processes and engineering choices converge. If we find more objects like 3I Atlas with similar compositions and behaviors, we will be forced to develop new criteria to distinguish accidental resilience from deliberate design. The presence of a high nickel shell will be the first clue, not the final verdict, in a more refined classification of interstellar artifacts and relics. There is also a philosophical shift hidden in this material story. For most of human history, Our sense of cosmic time has been tied to stars, galaxies, and orbits. 3i Atlas invites us to think instead in terms of material lifetimes. How long can an alloy hold its structure under bombardment? How long can a hull carry its shape across the slow abrasion of the interstellar medium? These are questions that sit at the intersection of astrophysics and engineering, and they hint that the true currency of long-term presence in the universe is neither light nor signal, but durability. In the quieter corners of research, some theorists already imagine a material archaeology of the galaxy. In that picture, civilizations come and go, but their most robust artifacts slowly accumulate: shells, sails, cores, and probes that no longer function as living systems, but still endure as distinct arrangements of matter. Objects like 3i Atlas would be the first hints of such a layer, a thin population of high nickel bodies that stand out against the background of ordinary rock and ice because they have not yet been worn down into anonymity. Viewed from that angle, the high nickel anomaly of 3i Atlas becomes less a threat and more a message about what is possible. It tells us that matter can be arranged into configurations that last far longer than our institutions, languages, or even our species. Whether those configurations arise from blind planetary evolution or from deliberate fabrication, they sketch out a kind of future for matter in which endurance is itself a form of memory. As you listen, you do not need to decide whether 3i Atlas is a natural relic or a technological one to feel the weight of that implication. Somewhere above the Earth, it continues on its path, a compact embodiment of a material strategy that prizes survival over spectacle. In the final chapter, we will bring that idea back down to the specific moment of December 19th, asking what it means for a world of water and rock to briefly share space with a passing hull of metal, and how we might face that encounter with curiosity rather than fear. In the nights leading up to December 19th, 3i Atlas will move through our predictions long before it moves through our sky. On computer screens and observatory whiteboards, colored lines will trace its inbound path, curving through the plane of the planets and threading between the orbits we know so well. It will look almost abstract there, just one more trajectory among many, a clean arc defined by a few numbers. Only when you remember what those numbers describe, a dense, high nickel body with a calm metallic skin, does the curve begin to feel more like the path of a presence. For most people on Earth, those days will feel ordinary. Weather will change, messages will arrive, traffic will move, and the sky will look the same as it always does, a pale blue in daytime and a scattered field of stars at night. The approach of 3i Atlas will not cast a visible shadow across cities or wake anyone with sudden light. It will remain a quiet object, small compared to the moon, tiny compared to Earth, and yet large enough in its own way to connect our planet to the wider interstellar environment for a brief moment. By the time December 19th arrives, the scientific story will have settled into place. We will know that 3i Atlas is not made of fragile ice, but of dense metal with an unusually high fraction of nickel. We will know that it carries broad radar bright facets and that it spins with a steady 16-hour rhythm. We will have traced its past passage near the sun and measured how little it changed there. The phrase dirty snowball will feel outdated. In its place will be a more precise description, a traveling hull of alloy, tuned by nature or by design for endurance rather than spectacle. Against that backdrop, it becomes easier to see the December 19th encounter for what it is and what it is not. 3I Atlas will not enter the atmosphere. It will not carve through the clouds or fire itself into the oceans. Its path will bend around Earth at a safe distance, crossing only the invisible structures that surround our world, the magnetosphere, the radiation belts, and the thin shells of charged particles that float far above the highest clouds. The real contact will happen there, in regions where only instruments and a handful of trained eyes routinely look. As 3I Atlas glides through those regions, the physics we have explored in this episode will quietly come into play. The high nickel alloy will act as a conductor. The motion of 3I Atlas through Earth's magnetic field will drive small currents along its skin. Those currents will, in turn, generate their own magnetic fields, briefly braiding with Earth's field lines before fading away again. Energy will be exchanged, but the exchange will be almost entirely electromagnetic and almost entirely gentle, a shifting of lines and charges rather than an eruption of heat and shock. For observers on the ground and in orbit, that gentle exchange will be an opportunity rather than a danger. If the sun is quiet, magnetometers may record tiny, well-timed ripples. Auroral cameras may see faint features brighten or drift in ways that line up with the predicted passage of 3I Atlas. Radio receivers may notice short-lived quirks as the ionosphere responds to small, localized disturbances. None of this will threaten power grids or satellites. It will be more like a controlled experiment that nature has arranged on our behalf, giving us a rare chance to watch a conductive body move through a planetary magnetic field. In that sense, December 19th is not a test of survival, but a test of attention. The planet will not need to defend itself from impact. Instead, our challenge will be to look closely enough to catch the subtle fingerprints of the encounter. If we succeed, the data will sharpen our understanding of 3I Atlas and of Earth's own magnetic environment. If we miss some signatures, the sky will not punish us. 3I Atlas will simply continue on its path, carrying its quiet hull back out into deeper space. For you, listening now, the question is how to hold this event in your own mind. It can be tempting to let imagination jump to worst-case scenarios, to picture collisions and disasters whenever a new object passes nearby. The evidence in this case points in a different direction. Everything we know about the orbit of 3I Atlas tells us that it will pass safely. Everything we know about its composition tells us that it will interact with our world through fields and currents, not through impact. The high nickel anomaly makes 3I Atlas more interesting, not more dangerous. That leaves room for a different kind of response, one based on curiosity and a quiet sort of awe. On December 19th, a body that has likely traveled for millions of years between stars will sweep past our planet just once, close enough for our instruments to feel its presence, but far enough to leave our surface untouched. We will, for a few hours, share a magnetic circuit with a traveler from elsewhere. Then the connection will loosen, and 3I Atlas will slip back into the dark, carrying whatever history is encoded in its alloy away from us again. As evening falls where you are, you might step outside and look up, even if you cannot see 3I Atlas directly. Somewhere beyond the limit of your eyes, above the thin air and drifting clouds, it will be there, following the path carved out in the simulations, moving through fields and sparse plasma. Under your feet, the solid earth will remain steady. Around you, familiar sounds will continue, wind and trees, distant traffic, the soft movements of your own home. The encounter will belong mostly to the instruments and to the long memory of the data they record. Later, as the night deepens and you prepare to rest, you can let the story of 3i Atlas become part of the background hum in your thoughts instead of a sharp one of worry. You live on a world that has withstood countless encounters, from ordinary meteors to storms of solar particles. This particular visitor has already announced through its orbit that it is passing by rather than falling in. Its high nickel skin and calm rotation are not warnings. They are simply clues about how matter behaves when it is built or selected to last. In the quiet before sleep, you can imagine 3i Atlas as a distant, slowly turning shape, already moving away along its outbound track. It is smaller than a moon and larger than the dust that streaks across the atmosphere as meteors. It is not here to change the course of human history in a single night. It is here as an example, a case study in endurance and in the subtle ways worlds and travelers can touch without colliding. As your breathing settles and your thoughts drift, the specifics of alloy ratios and rotation periods can fade. What remains is a softer understanding. The universe is not only a place of violent impacts and sudden catastrophes. It is also a place where encounters can be gentle, where a planet and a passing hull can share fields and currents for a moment and then move on, each unchanged in any way you need to fear. Above you, the sky will still be there tomorrow. Somewhere out beyond it, 3i Atlas will be a little farther along its path. You can let that thought be a kind of reassurance. The same physics that carries 3i Atlas safely past Earth also keeps your planet on its stable orbit around the Sun and keeps the Sun shining with a steady output that has allowed life to persist for billions of years. In that long, calm context, one high nickel visitor is not a threat, but a reminder that there are other journeys happening alongside our own. You are sharing the cosmos with objects that have crossed distances you will never need to travel. So as you close your eyes, you can imagine yourself not as a bystander to some looming crisis, but as a quiet witness to a graceful flyby. You and 3i Atlas are briefly part of the same story, joined by invisible magnetic lines that loop from your planet out into space and back again. The moment will pass, the data will be saved, and the night will return to its usual rhythm. You can rest inside that rhythm, knowing that when you wake, the world will still be here, turning steadily under the same sky, with one more mystery now a little better understood.